Hello, everyone. We're going to do this as a little bit of a tag team. And because Fatima has the vast majority of the slides, I'm going to let her drive while I just go through a couple of things at the beginning, and then I'll turn it over to her for the bulk of the talk. So I'm Eli Dart. I'm part of the science engagement team at ESNet. Fatima, you want to introduce yourself real quick?
Sure. Hi, everyone. I'm Fatima. I am security engineer and part of the security engineering team at ESNet.
Okay, so let's get started. So I'm just going to talk a little bit about the strategic framing in which we find ourselves, and that frames the context for this talk. So we've got on the order of a decade of experience now on Science DMZ broadly across the scientific community. And I think, from my perspective at least, I think we've learned several things. One is to first order, the Science DMZ does what it says on the can, right? It works to first order. It allows us to move data much more easily, in many cases more securely than we otherwise would be able to if we had to keep jamming this stuff through enterprise firewalls and poking holes in our normal enterprise perimeters to try to make large-scale data transfers work in that context. It's also possible and becoming increasingly common to build larger structures on top of the Science DMZ. And so I'm going to talk a little bit about that as well. And then another thing that's sort of clear is that some aspects of the Science DMZ are actually harder than others. And security is actually one of the parts that are harder than others, hence this talk. So in terms of larger structures, right, we've seen clustered Globus DTN deployments in Science DMZs as sort of a common design pattern. We've seen data portals that in some cases use those clustered deployments or interact with them as a common design pattern. But all of these things have to be operated safely or they cannot be operated at all in today's internet environment. And so security is a critical and also a challenging component in all of this. So next slide, please. So if we look at the types of things that one can do with these things, right? DTN clusters, for example. This is just a random vignette, some screen grabs from the ESNet portal. This was a Harvard physicist moving data from Oak Ridge to NERSC. He'd gotten an allocation at Oak Ridge to do a very specific, very large-scale calculation on the big machine there. This was transferring the results, some of the results of that calculation back to NERSC, where the rest of the collaboration had room to run. And so this was just the user going clicky, clicky in the Globus GUI, kick off a couple of jobs. During the transfer, the Oak Ridge facility had a previously scheduled maintenance. And if you look at, so on the one hand, or you look at this, right, the traffic peaks are 80 gig high. Okay, so they were moving along at a good clip. Total data volume is almost 3/4 of a petabyte, and nobody had to take, nobody had to account for anyone else in doing the work that they needed to get done. Oak Ridge folks hit pause, did whatever they had to do, unpaused it, everything kept on back going again, no problem at all, right? So this is the kind of capabilities you get with modern tooling, right, built on top of the Science DMZ model that makes scientists much more productive than they would be without it. Next slide, please. So here's another example where you have a large-scale DTN cluster talking to a portal that runs on that DTN cluster. So this, is it talking to a portal? No, I think this was going to feed their portal. Anyway, so this was a bunch of data moving from Argonne, the supercomputer center there, to NCAR. So this is now calculations run at a DOE facility being transferred to an NSF facility, right? Again, the traffic peaks there are on the order of 50 gig high for the data transfer. And so again, this is just like routine. This has become routine, normal stuff, which is exactly what we want. So next slide, please. So the idea there, right, this portal idea using the Science DMZ model, right, is an example of this larger structure, right? You bolt a web-based sort of search and discovery interface onto a data store that is front-ended by a DTN cluster. And if you go one more, we're seeing a proliferation of these. Next slide, please. We're seeing a huge proliferation of these data portals now. They're cropping up everywhere. It's a really sort of productive design pattern built on top of the Science DMZ model. So next slide, please. So there's a huge advantage to this, right? As these examples illustrate, right? There's a huge advantage to this if we can actually get it deployed. Right, so the goal here is to get this into the hands of the scientists so that they can be productive. But I will say again, we cannot deploy something unless we can operate it safely. And the scientific promise in the Science DMZ model and in the larger scale structures that we can build on top of it hinge on our ability to deploy them and operate them safely, right? And so that's now what Fatima is going to talk about, because security keeps coming back as a common sticking point, and it's something that a lot of folks struggle with. So Fatima, I'm going to stop talking. I'm going to hand it over to you.
Thanks, Eli. So, alrighty. So a lot has been talked about the Science DMZ and security architecture. So I'm just going to go ahead and jump right into the securing, how to secure the Science DMZ and how you can build a secure architecture around Science DMZ. So the goal of Science DMZ security is to disentangle security policies and enforcements for science flows from those required for the business systems, right? So you need to understand what you are trying to protect. And Science DMZ networks and Science DMZ environments are different from the regular business or enterprise environments, and hence have their own different needs for security policies and procedures, and they should be followed in order to protect them. And the narrower the footprint on the network of the various services, it's easier to detect an anomaly and protect those services and contain them and control them, right? So separation is the key, and we will be talking more about how different kind of network segmentation together with other key components of the secure architecture would help you overall protect your Science DMZ network. So assessing the risk. So once you know what you're trying to protect, you can then assess the different types of services and areas for various kinds of risks based on the risk appetite, right? So if your risk appetite is to accept certain kinds of risk based on the assessments you have done on certain services, then you can accept them. But for certain kind of services, if you feel like the risk is higher, then you have to implement the controls, security controls to mitigate that risk. And then accept the residual risk. And you have to take into the consideration that not all types of data, that the research data is same, right? So you should talk to your researchers that maybe there is some kind of research data that needs more protection and more containment than the other kinds. So based on that assessment of what different kind of data is flowing on your Science DMZ network, you can accordingly implement the controls to secure it. And again, applying access controls can increase your cost. So depending on how much containment and control you want on the certain kind of data, it might have a performance impact based on what kind of security control you have put into place for mitigating that risk. Okay, so now securing Science DMZ. So now how can you protect Science DMZ? We have talked about what you are trying to protect and what kind of risk you are trying to assess in different kind of data transfers that are happening on your network, right? So now actually dealing into how you can protect the Science DMZ. So it should be viewed as a security architecture. That means when deploying your Science DMZ, security architecture should be kept into the mind. Like from the very start, you should think about how you can deploy your Science DMZ in a secure way, right? So reduce the degrees of freedom and number of network devices in the path that cannot perform and keep your path as clean and simple as possible. Your network is as fast as the slowest device on your path. So make sure that all the devices that cannot perform on that high speed are not in your path and not behaving as a bottleneck and bogging down the performance single-handedly in your network. the cleaner your Science DMZ network is, the better it will be to secure it and make it more performant. And again, your Science DMZ network should be able to support the specialized scientific applications as well, like virtual circuits and distributed control systems. Okay, so talking about the first key control for securing the Science DMZ is the network segmentation. So network segmentation means separating out the science flows from your normal enterprise network flows. You will have better control over how you want to handle the Science DMZ traffic hitting your enterprise network with the network segmentation, and it will help clear the data paths for science and non-science DMZ traffic. And you would be able to deploy better security controls based on the requirements of Science DMZ versus enterprise network. Another key important thing about segmentation is it allows you to implement zero trust model for your Science DMZs. That means your enterprise doesn't have to trust your Science DMZ network, and it is treated as the outside the perimeter for most of the campus services. And then you can have kind of like a controlled trust between the zero trust network between your Science DMZ versus your enterprise network, and consider it as like the internet traffic or outside traffic, and your enterprise can kind of like have the policies that you have for your normal internet kind of traffic. Okay, so the access controls. One of the important security controls for Science DMZs is ACLs, access control list, right? And in fact, according to the NIST 841, a router with an ACL is considered as a stateless firewall, which means you don't need to have heavy performance intensive application layer firewall that is doing deep packet inspection of your data traffic, because the Science DMZ traffic is pretty simple, right? It's just data transfer traffic. So unless you have like a true need to do the deep packet inspection of those traffic flows, you don't really need to have that kind of firewall that is bogging down your performance. So yeah, so for Science DMZ, just a basic simple router ACL can do the great job of filtering out all the unwanted connections and unauthorized access you need not to have in your Science DMZ network. So just a layer 3, layer 4 filtering would go a long way, like source IP, source port, destination IP, destination port, and protocol. That kind of filtering will get you to a really good and secure place in terms of securing your overall Science DMZ traffic. And again, you can do a lot of things with ACL control, right? You can block the access to your control plane. You can implement a default deny on your access control list. That means don't allow traffic to unwanted protocols in your Science DMZ, or the protocols that are well known for the exploits and malware transfers on your network. So yeah, Science DMZ also supports the model of default deny just by implementing the right kind of access control on your network. Firewalls continue. So if you have to have a firewall that like you are either bounded by some kind of mandate, and if there is something, some policy that requires you to have an application layer next generation firewall, then make sure you test it. Make sure you test the performance with and without it, and if on your clean path. So don't put anything else, and just do an intense testing and see if you can accept the performance hit by having the firewall in your path. And it would be great if the next generation firewalls can actually support elephant flows, because that is the majority of the time Science DMZ networks are bogged down because of the elephant flows, and application layer firewall not able to keep up with those kind of flows because it constantly is doing the application layer filtering by default. So it would be great if we have the firewalls, if we have the next generation firewalls that can perform that are friendly with the elephant flows, but unfortunately we do not have them right now. So if there is a need, make sure you test it and make sure it's acceptable in your environment, the performance hit that it will come with by deploying the next generation firewall in front of your DMZ hosts. Another really elite way to do the filtering and to get away with all kind of like unwanted traffic is deploying the host-based firewalls. It is one of the vital layer of defense that you can put in your Science DMZ, because many times if you have some loose or misconfigurations in your ACL, then the host-based firewalls will kind of like come into the picture, and they will act as the second layer of defense, because if you have narrowed down that what services and what applications are running on your host, and these are the only ports that should be allowed in and out, then host-based firewalls can actually be a very elegant way to deny all the unwanted access in your Science DMZ. And yes, they do work, and then they do perform. So, and there are two kinds, like NF tables and IP tables, but NF tables are preferred more on the Linux systems nowadays than IP tables because they're more performant. So yeah, make sure that you actually utilize and take advantage of host-based firewalls as well as one of the lines of defense in defending your Science DMZ network. Okay, contains the fourth key aspect of securing your Science DMZ is contained services and applications. So as mentioned before, that Science DMZ networks are very specific and they're designed to serve a very specific purpose. For example, Science DMZ networks, one of the main function in Science DMZ networks is data transfers, right? High rate data transfers, and there are very few applications that are used for those kind of high rate data transfers. So unless you have absolute need of any other application other than the data transfer functions, then you should not have those applications running on your hosts that are taking part in your Science DMZ network. Like for example, Science DMZ should not have like user services like email, web, blogs, and whatnot. So non-DTN kind of stuff, you should not have that running, and that also mitigates the risk of having a lot of attack surface exposed. So the more you have, the more you have to protect. So the less you have and the limited contained services you have, the lesser the attack surface will be, and the lesser amount of applications you would need to protect from the unauthorized access. So make sure that you keep the applications contained and the lower amount of applications running on your host. Patch the software and run up-to-date version or up-to-date and stable version security-wise. Up-to-date version of the software on your host. So that's another key, that if you're running applications, make sure they're stable and make sure they have all their patches implemented and deployed. And the other thing that is not considered very not considered in a very high regard is network security monitoring, and it is important, right? Because you should be you want to keep an eye on the network traffic to make sure that all the security controls are working the way you have set up and they are working correctly, right? So, and if there is any kind of misconfiguration and you are seeing any unintended application that you are not supposed to see, then it will infer that there is some kind of like risk in the network, right? So network security monitoring provides just that you make sure that what you are expected to see, that's what you are seeing in your network traffic, and any other application that pops up all of a sudden that is not in your cleaned or checklist of the applications that should be running in your Science DMZ, then you can take another step of what changed or what's going on your network. The two main components in the most R&D entities that are used nowadays for network security monitoring are Zeek and Snort and Suricata. So Zeek is basically a passive network security monitoring system that just sits on your network, and then it just sees the net. It just gives you a holistic vision of what's transpiring on your network. It processes the packets and then it produces the events that are like human readable and human digestible. So it gives you an amazing view of what is transpiring on your network, and it generates a lot of different log files. And one of the important log files it generates is known services and ports. So if you see a new port or new application that is popping up on your network that you have no idea about, then that network security monitoring can give you a clue that maybe something opened up on your firewall, or maybe there is something unintentional going on in your network that you should check it out. So network security monitoring plays an important role in making sure that all the other security controls that you have in place, like router ACLs and host-based firewalls and filtering, they are working in the way they should be. So, and Zeek/Portlight is the commercial version of Zeek. It kind of like gives you that best holistic passive network security monitoring view of your network. Signature-based IDS, Suricata and Snort are signature-based. They come with their own signature database and DAT files, and they look for certain patterns in your traffic, and whenever they see that kind of pattern, they trigger an alert saying that, hey, I saw this event happening and I saw this kind of malicious traffic going on in your network. So network security monitoring is also another great key component of having a secure Science DMZ architecture. Okay, so other than that 5 things that we have discussed, there are other things that you can consider for securing and having a secure architecture for your Science DMZ. The first is limited routing, right? So you can define what subnets and IP ranges you should be routing your traffic to and from your Science DMZ. For example, ESNet DTNs only route to known RNA entities and AWS, and that's the link that you can see the sample configurations on. Outbound ACLs, just like inbound ACLs, where you are blocking the unwanted access from some of the ranges or to some of the ports, you can actually do the outbound access control as well. For example, just limiting your route to some of the limiting your routes to the IP addresses and subnets that your Science DMZ is supposed to contact and connect to. Implement black hole routing, BGP flow spec and community feeds. They are a great way to control. They are a great way to mitigate attacks like DDoS. And if you have an IP, if you have IP addresses and that are not behaving correctly on your network, you can actually use BGP flow spec to null route them. So black hole routing is another great security implementation that you can have together with those 5 key factors that we have discussed so far. Automation and central management, of course, if you have a deployment that has a lot of account management and software patching, so it's good to have it automated. So automation and central management also again plays a part in easing down in the maintenance of your overall Science DMZ architecture. This is the slide with all the security components that we have discussed with the network segmentation, where the network segmentation would look like, how the network segmentation would look like, where is the ACL control placed, and how it looks like in the overall architecture. Host-based firewalls, contained services, and network security monitoring. So those are the 5 key components that we have discussed in securing your Science DMZ. So this is like an overall picture where you can picturize that, where exactly that control goes on your network and how it looks like. Okay, so for conclusions, consider Science DMZ as an integral part of a good risk-based security posture for the entire institution. Science DMZ separation and network segmentation from the enterprise network is a key. Think of Science DMZ as a security architecture and work with security team to implement a well-designed Science DMZ and understand what you're trying to protect and design the security controls around it to mitigate the overall risks. So that was the conclusions, and thank you so much for attending, and we are happy to have any questions that you guys might have.
So there are a couple of questions in chat. I answered one of them, but you may want to take a look at the couple that are there.
Oh, okay.
If you're not able to bring up that interface, I can read them off to you.
Yeah, I can just see a couple of comments on chat. Oh, Q&A. Okay. Oh, so so the question is, do you utilize any internal transparent firewalls without IP addresses on their interfaces and capture traffic flows in order to stop traffic without detection by an attacker? Currently, no, but I haven't had a lot of experience with internal transparent firewalls, but I will take a look into that.
Another thing to remember here, right, is that there are a lot of different contexts for this. So ESNet as an RNE backbone, we're not going to deploy that sort of thing, right? But now, as a research group on a campus, you know, you totally could deploy that sort of thing, right? It also may be so I mean, some entire campuses operate bump in the wire firewalls, right? So there's a whole suite of technologies here, and as Fatima said earlier, right, the thing you need to do is, you know, if you have to have a firewall in the way, you better characterize it and you better understand what it's going to do. And if you can get away with not having a control plane that's not engineered for performance in the data path, right, and solve that problem a different way, it's much more likely to be performant. It's more likely to be deterministic, right? As she was talking about at the beginning of sort of removing complexity, removing degrees of freedom, right? So there's this huge toolbox that's available. Part of the reason for deploying the Science DMZ is to say, okay, how can we do this in a way that is deterministic, performant, easy to deploy, right? Easy to operate, and with enough reduced complexity that we can actually apply performant security policy enforcement mechanisms and so on. Sorry, Fatima, it sounded like there might be a larger context there, so I just wanted to provide that.
No, that's great context. Thanks, Eli. And the other is just a comment that pfSense is one type of firewall that can be configured as a transparent firewall and export the traffic flows via the management interface.
Right. I mean, so yes, pfSense is great for the things that it's great for. I would not recommend putting that on a multi-hundred gig campus perimeter. Other questions?
I think those were the open questions I had.
One more just came in.
Yeah. So is there concern with the elephant flows with the integrity of the data, such as detecting when there are bit flips? Absolutely. So actually, Fatima, you've still got the slides up. Can you go to the Oak Ridge transfer example? Yeah. So in fact, in both of those jobs, there were multiple random, not systemic, just random bit flip data corruption errors. And Globus handled those seamlessly inline, right? And so what that meant was the user didn't have to then go do a data integrity pass manually over 3/4 of a petabyte of data, roughly 2 million files-ish, right? And so, yes, especially as data sets get large, that's totally a thing. We've also seen as hardware fails, sometimes it ceases operating correctly, and if it doesn't fail all the way, you can systemically get bit flips. We've also seen this in firmware bugs. The Linux kernel, older versions of the Linux kernel under memory pressure would do this, right? So there are integrity problems throughout the stack, and so having a tool chain that verifies the integrity of the data placement operations that you do is actually really, really important. And so thank you for bringing that up, Mark. That is totally a thing. And yes, it's important. And what you'll find is that modern tooling, right? Globus does this actually all the way to the file system. Aspera does it memory to memory. Modern data transfer tooling will solve this problem for you. Well, it won't solve it. It will dramatically reduce the scope for silent corruption. Other questions? Okay, if we're good, then it's back to you all, I think.
Thank you both so much.